In the previous lecture, we have seen the calculation of the eigenvalue and eigenstate or eigenfunction of two operators. And those two operators were the operators j square and jz. And you have seen in the previous lecture that kate jm is actually the eigenstate of both of these operators, and their eigenvalues we have obtained in the previous lecture in this way. And you know that the eigenvalue of the operator j square is j times j plus 1 into h bar square, and the eigenvalue of the operator jz which we have obtained in the previous lecture was mh bar. So I have mentioned here that result which we have discussed in the previous lecture in detail, and you can see actually these two equations are the eigenvalue equation of the operators j square and jz. Here kate jm is the eigenstate of both of these operators, but their eigenvalues are different. Eigenvalue of j square is j into j plus 1 into h bar square, and that of jz is mh bar. Now in this lecture, our aim is to show that this j plus kate jm, this is a new state in fact, and this is also an eigenstate of the same two operators j square and jz. Kate jm, you have already seen that kate jm is the eigenstate of operator j square and jz, but in this lecture we are going to see that when we operate the operator raising operator j plus on kate jm, then we get a new eigenstate, and this eigenstate is an eigenstate of the operators j square and jz. But what will be the eigenvalues in this case we will also see here. Now as you know, you have learnt in the previous lecture that the operators j square and j plus commute with one another. When you say that j square and j plus commute, what does it mean? It means the commutator of j square and j plus equal to 0. And so you can say that commutator of j square and jz is 0, j plus is 0. So you can write from this commutator that j square times j plus minus j plus j square is equal to 0. And so this j square j plus is equal to j plus jz square, j square. So when we will operate on this eigenstate j plus kate jm, this operator j square, what will be the result? You can see, since we have seen here that j square j plus is equal to j plus j square. So here j square j plus can be replaced by j plus j square. So j square operated on j plus kate jm can be written as j plus operated on j square kate jm. From this result it is evident. Now you know, you have seen in the previous lecture, I have mentioned it here, that the eigenvalue of the operator j square is j times j plus 1 times h bar square. So j square operated on kate jm is equal to j times j plus 1 h bar square kate jm. You can see here. And now since j times j plus 1 h bar square is just a constant, so let us take it outside of this operator and operate this j plus operator on the state kate jm. So you get that when j square will be operated on the eigenstate j plus kate jm, our result is what? This is j times j plus 1 times h bar square and j plus kth jm. You can see this equation here. This j square is an operator and j plus operated on kth jm is an eigenstate. And when this operator j square is operated on this eigenstate j plus kth jm, we get this much. So this equation 1 is nothing. This is simply the eigenvalue equation of the operator j square when the eigenstate of this operator is j plus kth jm. And you can see that the eigenvalue of this operator is again found to be j times j plus 1 h bar square. So this is a very interesting result, that when the eigenstate of the operator j square is kth jm, then its eigenvalue is j into j plus 1 h bar square, and also if the eigenstate of this operator is j plus kth jm, even then you see that the eigenvalue of this operator j square remains same, that is, it is again j times j plus 1 h bar square. So in this way you can say that this state j plus kth jm is also an eigenstate of the operator j square with the same eigenvalue j times j plus 1 h bar square. Now actually we have to find the eigenvalue of the operator jz when it will be operated on this new quantum state j plus kth jm. So we have to now show the action of this jz on this j plus kth jm. So first of all we write the eigenvalue equation. Not eigenvalue equation. I have just operated this jz on this new state j plus kth jm. Now you know that jz j plus operated on kth jm is simply written like this, jz j plus kth jm. Now we will find the value of this operator jz j plus by this commutation relation. You have seen in the previous lecture that the commutator of jz and j plus does not vanish, but the commutator of jz and j plus is equal to h bar j plus. We have just seen this thing in the previous lecture. Now commutator of jz and j plus, from the definition of commutator you know this is written as jz j plus minus j plus jz, and that will be equal to h bar j plus. And so from here you can obtain the value of the operator jz j plus. This jz j plus will be what? This will be simply j plus jz plus h bar j plus. Now we will use this result which we have obtained in this equation 3 in equation 2. So this jz j plus in equation 2 will be replaced by this expression j plus jz plus h bar j plus. So you can see here I have actually replaced in the RHS of this equation 2 jz j plus by this expression j plus jz plus h bar j plus. So this is operated on kth jm. Now operate j plus jz on kth jm and h bar j plus on kth jm separately. So you can see here that this is j plus jz operated on kth jm plus h bar j plus kth jm. This is just a simple algebra. Now you know the eigenvalue of the operator jz is mh bar. So jz kth jm, this will be simply mh bar kth jm. So since mh bar is a constant factor, so I have written it here outside of the operator. So this is mh bar j plus kth jm. And this second term remains at each. Now in RHS you can see that we can take m+1 h bar as a common factor, and this will be m+1 h bar times j plus operated on kth jm. So you can see this equation 4 is nothing. This is simply the eigenvalue equation of the operator jz when its eigenstate is j plus kth jm. So here kth jm is not the eigenstate, but we have a new eigenstate of this operator jz, and that eigenstate is what? That is j plus kth jm. And so you can see from this equation that the eigenvalue of the operator jz in this condition is not mh bar, but it is m+1 h bar. You can see the difference. The eigenvalue of operator j square even when the eigenstate was j plus kth jm remains same. That was simply j into j plus 1 h bar square, as you have seen in this equation. You can see it here. But for the eigenstate j plus kth jm, the eigenvalue of the operator jz does not remain same. When the eigenstate was kth jm, then the eigenvalue of operator jz was what? You know, that was mh bar. But now you can see for the eigenstate j plus kth jm, the eigenvalue of the operator jz is not mh bar, but it is m+1 h bar. So you can see that in this condition, the eigenvalue of this operator jz has been increased by 1 unit in the unit of h bar, or you can say that it has been increased by h bar. So this is the effect of j plus operated on kth jm. So from these two results we conclude that j plus kth jm can be written as a constant c kth jm plus 1, because eigenvalue has been increased by 1 unit. So you can see instead of m we should now write m+1. But what is the value, actual value of this constant c? We will now obtain it. In fact, to obtain the actual value of constant c, we will do a simple algebra. You can take the scalar product of this equation 5 with itself, and then you will see that the value of c can be found. So to find the value of c, we take a scalar product of 5 with itself. So take the scalar product of this equation 5 with itself. In fact, I am writing the terms in RHS in LHS for convenience. So you can see this c times c. We will write it mod of c square. Mod of c square, and a scalar product of j m+1 with j m+1, and this will be equal to. Now see the LHS, which I am going to write in RHS. So this will be what? We have to take the scalar product of what? J plus Kate JM. And Kate JM, and again J plus Kate JM. J plus Kate JM. We take the scalar product. Now you can see what will be the scalar product of Jm plus 1 with Jm plus 1. As you know that Jm plus 1, this is actually normalized. So this scalar product of Jm plus 1 with itself will be equal to 1. So this will be equal to 1. So you can write C square equal to. Now you know that the operator J plus and J minus, that is the raising and lowering operators, are not Hermitian. We have learnt in the previous lecture this thing, that J plus operator, which is called raising operator, and J minus operator, which is called lowering operator, these are not Hermitian, but they are actually Hermitian adjoint of one another. So J minus is the Hermitian adjoint of J plus, and J plus is the Hermitian adjoint of J minus. So this scalar product in the RHS of this equation can be written as in this way. You can see, we can write J minus J plus. J minus is the Hermitian adjoint of J plus operated on Kate Jm. Why I have written like this? Because just I have told you that J minus is the Hermitian adjoint of J plus. So you can say as J minus is the Hermitian adjoint of J plus. So I have written this expression in this way. Now we will obtain this operator J minus J plus first of all by the commutation relation, and then we will solve it. So now you can see J minus J plus. From the definition of the lowering and raising operator, you know this J minus is equal to what? This is Jx minus Ijy, where I is the iota, you know, times J plus, and J plus is what? You know, this is Jx plus Ijy. So let us now take the simple product. Jx times Jx, this is just Jx square. Jx square. And minus Ijy times Ijy. This will be minus I square jy square, but I square is minus 1. So minus minus will become plus. So this will be what? This is simply plus jy square. Plus jy square. Now take the product of jx with ijy. So this is plus I jx jy. And then take the product of minus ijy with jx. So this is minus I jy jx. Now you can see this can be written as jx square plus jy square and plus I jx jy minus jy jx, minus jy jx. And you can see this can be written as jx square plus jy square plus I. And what is this? You can see this is nothing, this is simply the commutator of jx and jy. So this is commutator of jx and jy. But as you know, the commutator of jx and jy is equal to what? You have learned this thing in the previous lecture. This is simply IH bar jz. So replace this commutator by IH bar jz, and so our result will be jx square plus jy square and plus I, and commutator of jx and jy, this is in fact I h bar jz, IH bar jz, and this will be equal to jx square plus jy square. Now I times I square, that will be minus 1, so here will be minus h bar jz, h bar jz. So in this way you have obtained that the operator j minus j plus is equal to this much. Now we will use this result in this equation. At the place of this j minus j plus, now we will write this expression jx square plus jy square minus h bar jz. So what is this equation? I have not written here equation number, so let us say this is equation 6. So equation 6 can be written as, you can see c square equal to, actually this is c square, and this will be bra jm and at the place of this j minus j plus, now we will write this much. This is jx square plus jy square minus h bar jz, and ket gm. Now we will simplify the RHS of this equation, and this is just a very simple simplification. You can see it here that this c square can be now written as, see here, this will be in fact bra jm jx square ket jm. In fact this will be split into 3 terms, and this will be bra jm j square ket jm, and again this jy square, and let us write this jx square plus jy square. As you know, this jx square plus jy square plus jz square, this is equal to j square, you know, and from here you can write this jx square plus jy square equal to j square minus jz square, So this expression jx square plus jy square minus h bar jz may be written as j square minus jz square minus h bar jz. So this expression can also be written like this. This is jm and j square minus jz square and minus h bar jz and get jm. You can write it. So here, in fact, now we will use this expression. So the first term will be jm j square jm, and the second term there will be minus, this will be minus jm jz square. I am not speaking always bracket and jm. And what will be the last term? In last term you can see there is minus h bar jz. So this can be written as minus h bar. This is a constant factor, and this is jm jz jm. You can write like this. Now you can see what is this. This is actually the expectation value of j square. This is expectation value of j square. And what is this? This is expectation value of jz square. And this is the expectation value of jz. Expectation value of jz. And you know, the expectation value of j square is nothing. This will be simply the eigenvalue of this operator j square, because that is fixed, and so that will this expectation value will be directly equal to its eigenvalue. And what is the eigenvalue of j square when its eigenstate is jm? You know that the eigenvalue of j square operator when its eigenstate is jm, this is simply j into j plus 1 into h bar square. So we can write this expectation value as j into j plus 1 into h bar square. Again, you know, the expectation value of jz, which will be jz square, not jz, which will be actually equal to the eigenvalue of the operator jz square. Since the eigenvalue of jz is mh bar, so the eigenvalue of jz square will be m square h bar square. So this is m square h bar square, and minus this is h bar times. Now see this. This is expectation value of the operator jz, and its expectation value will be again equal to its eigenvalue, which is mh bar. So this is mh bar. Now you can see that this will be j square plus j h bar, sorry, you can take this h bar square as a common factor. H bar square as a common factor. So see here, this is simply j square plus j minus m square and minus m, and I have taken h bar square as a common factor. Now you can see, we can write this in this way. This is j square minus m square plus j minus m times h bar square. Now this j square minus m square, this can be written as j minus m times j plus m, and plus you can see here, this is j minus m, and the common factor is what? This is h bar square. So you can take this j minus m as a common factor, and here there will be j plus m plus 1, j plus m plus 1, and times h bar square. Actually this is a c square, and therefore we can take, if we take the real positive value of this c, then this c will be simply equal to a square root of j minus m times j plus m plus 1 times h bar times h bar. You can see it here, times h bar. So this is actually the value of the constant c, and let us say this is equation 7. So you can see when the operator j plus will be operated on ket jm, see this equation 5, then what will be the result? At the place of c, now we will write the value which we have just obtained. So when we will use the value of c in this equation 5, then this equation 5 will become what? You can see, therefore j plus operated on the state ket jm, this is equal to a square root of j minus m times j plus m plus 1 times h bar and ket jm plus 1. So actually this is the new state. When we operate the operator j plus on the state ket jm, we get a new state, and this new state is equal to this much. You can see it here. So in this discussion you have learned several important facts. First of all, you have seen that j plus ket jm is also an eigenstate of the operator j square and jz, having the eigenvalue same for j square but a different eigenvalue for jz. In case of jz, the eigenvalue is increased by h bar, and this new state can be expressed like this. In fact, this result is very important for the competitive examination. If you will see the previous year question of civil services physics optional paper, you will find that this result has been asked at several times directly to prove. So if you are preparing for the examination like civil services, then this derivation will be very important for you. And this result or this new eigenstate concept is also very important for other competitive examination for objective problems. How the eigenvalue and eigenstate changes by the operation of j plus on ket jm. So this discussion is not important only for university examination but for various prestigious competitive examinations.